Okay, hello everyone. Good morning, all of you. So we'll start with the quote, and it's by Oprah Winfrey. And she says, be thankful for what you have. You will end up having more. If you concentrate on what you don't have, you will never ever have enough. Because nobody will have everything and nobody is God, right? So everybody will have some things with him, and many things will not have. So if you see what you have, you will be always happy. If you see what you don't have, because there will be always, so you will never be happy. And today is the birthday of Blue Ford. He is a black American astronaut who was the first black astronaut when he went into space on 30th August 1983 aboard the Space Shuttle Challenger. He next was on the Challenger crew of the German D1 Space Lab mission, and his third and fourth flights were on the shuttle Discovery, and he became a NASA astronaut in August 1979 and spent a total of 688 hours in space. During this time, his NASA biography lists that his technical assignments included, you can see his expertise, working with space station operations, the remote manipulator system, space lab systems and experiments, space shuttle systems, payload safety issues, and verifying flight software in the Shuttle Avionics Integration Laboratory and in the Flight Systems Laboratory. So such is the expertise. So he says he is a US aerospace engineer, retired US Air Force officer, fighter pilot, former NASA astronaut, and the first black person in the space. Okay, so today we will have the class on turbulence modeling. And okay, it's a huge subject actually. It's offered as a separate subject in some of the IITs and advanced institutes. But we will have a brief discussion of that. I will give you a gist, and so that later you can, because you are going to do most of the 90% of you are going to do CFD projects only. And when you do CFD project, you are going to bound to use turbulence modeling. Okay, some model you are going to use. Okay, you may not need anything to know when you apply modeling because it is a package usually. You just click in some model and some result you will get. But when you go out or when you go for an interview or something like that, they will ask you, okay, which turbulence model you have used, why you have used this, and what is that behind it, or something like that. You should have some idea about the turbulence modeling. Okay, uh, so just we'll see what is the outline. We'll see what is turbulence, why study turbulence, characteristics of turbulence, movement in the study of turbulence, and approaches to predict the turbulent flows, scales of turbulence, Reynolds averaging, Rand's equations and unknowns, Reynolds stress equations, closure problem of turbulence, characteristics of wall-bound turbulence flows, turbulence models and ranges of applicability. Okay, these are the things briefly we will just go through. Okay, you can always ask me if there is any doubt. You can stop me. Okay, so what is turbulence? It is an unsteady, irregular, aperiodic motion in which transported quantities like mass, momentum, scalar species fluctuate in time and space. Okay, there will be fluctuations in all the variables, and there will be unsteady and completely even irregular, right? Irregular, random, like that. And the identifiable swirling patterns characterize the turbulent eddies. Usually, turbulence is involved with turbulent eddies, and there will be enhanced mixing. Matter, momentum, energy, everything gets mixed. And as I told many times, friction is good or bad. Okay, some many times we don't want to have the friction, but without friction you cannot live. In the same way, heat transfer, whether you want to have or not, sometimes you want to enhance the heat transfer, sometimes you want to reduce the heat transfer. In the same way, turbulence, whether you want it or not, sometimes we want to have turbulence and sometimes we want to reduce the turbulence. Okay, suppose if you take an IC engine or a turbo machine, gas turbine, combustion chamber like that, and if you want to have a complete combustion there, I should have thorough mixing, right? So there I create turbulence by keeping swirlers and modifying the design of the combustion chamber and all. I want to create turbulence and eddies and all mixing. I should have better mixing. And many times I want to reduce the uh, mixing, right? Or eddies and other things. Suppose if you have a bluff body, if there is a flow over a bluff body, you have seen that there will be vortices and all, and there will be big wake. And this wake creates drag on the system. And I want to reduce it. So for that, I make it streamlined body so that I can reduce the eddies and separation and all. And because of that, I can reduce the drag. Okay, so sometimes I want, and you might have seen that there will be some scenes on cricket ball. Okay, so we do that to create turbulence, right? When the ball is pass on to the batsman. So what happens is at low velocities also I can create, because that creates separation, that creates turbulence, and because of turbulence in the bluff body, right, the drag reduces. Okay, this is interesting. Sometimes in the bluff body, I want to create turbulence. In the laminar, the streamlined body, I want to avoid the turbulence. So it depends on what type of drags you have. There are, I think I explained you, there are two types of drag, friction drag and pressure drag.
So, so due to turbulence, the eddies formation takes place, and eddies creates
Yeah.
we can say.
So what happens is when you take a bluff body, that is bluff body means it's like ball like thing. Okay. So if I have like this, and if it is a laminar flow, it gets separated like this, and there will be vortices this way. Okay, this is laminar. And so here large wake and large drag. And so what people do is here wherever it is going to be separated, and here I keep that seam like thing. Okay, that threads like thing. So you have seen a rough surface on that, right, at a particular annular space. So what happens is when it is just getting separated, because of this, it gets mixed up, right? And because of that, it delays separation. Okay, instead of going separated there, it will become like this. This is turbulent
Sir,
diagram. Yes,
sir, mixing means
that is low velocity and high velocity particles. They get mixed up, and even everything gets mixing, right? Suppose mixing, I say, suppose if combustion chambers are there, air and fuel are there, I should have better mixing so that I will have better combustion.
sir, mixing means I
Right
don't
here in the
understand.
boundary
What type of?
in the boundary layer, there will be boundary layer, some fluid will be there, and free stream there will be some fluid, and if they get mixed up, right, so that is called mixing. And sometimes if you have a jet coming out of a nozzle, right, that is also called mixing of that flow. So here turbulent flow reduces wake region and drag. So I create turbulence here. But if I have a streamlined body, I don't want to have turbulence, right? Because there is drag is equal to pressure drag plus friction drag. So pressure drag is due to wake and separation and the eddies like that. Friction drag is due to just friction on the surface, right? So on the bluff body, pressure drag is large and friction drag is small. So I want to reduce this, right? reduce by creating turbulence. But if I have streamlined body, pressure drag is less because there is no weight, small weight, and the friction drag is more. Okay, so I want to have laminar only. Because turbulence increases the friction. Is it clear?
Yes, sir.
Okay. And okay, why we are interested is all natural flows are turbulent. Okay, all natural flows are turbulent, and whatever we are doing till now, we are solving all laminar equations. They give values, but not accurate values. Okay, so approximately it will give some, because as I told many times, why we go for numerical methods, though they give approximate results, because I am happy with approximate. I need not worry about exact results and struggle myself, because we always give some factor of safety and all. Okay, and that's why people manage with laminar flows as long as they could not solve the
So
turbulent
please
flows.
repeat. Actually, there was some internet issue, so
Okay, okay,
voice
okay.
was lost.
So what I am telling is, as an engineer, we are not worried about the exactness of the result. We are happy with approximate results, because finally we are going to give some factor of safety and we are taking care. Okay, that's why we are doing numerical methods, though they don't give me uh, exact results. Okay. In the same way, as long as people found turbulent flows are difficult to solve, right? Then we are satisfied with laminar results, and we are doing the designs. But once we have the high-speed computers available, so then people thought of why not solve turbulent flows. Okay, what is the problem with turbulent flows? And before going for the problem with the turbulent flows, we will see what are the characteristics of turbulence. And it is completely random and fluctuating and highly diffusive and highly dissipative and it is highly 3D and full of vortices and the another main important thing is wide range of uh, length and time scales. Okay, this is the particular important thing. Wide range of length and time scales. Okay, what do we mean by this? And so here the equations are same. For laminar and turbulent flows. They are Navier-Stokes equations. Okay, same equations are to be solved. Then what is the problem? Okay, the problem is the scales. Okay, what do we mean by the scales? And before understanding the scales, we call what is called as there is what is called as energy cascade. Okay, so turbulent flow needs more energy. Okay, if I want to have a pipe flow with turbulence, right? So it needs more energy for pumping. And this energy is passed to the largest eddy. So biggest eddies, whatever are there, that will take the energy. And these eddies get stretched and split into smaller eddies. So energy gets passed on from the largest eddy to the smallest eddy, and this is called as energy cascade. And finally gets dissipated as heat by viscous dissipation. Okay, so whatever energy is given, it will be taken by the largest eddy. The largest eddy size, even in a pipe flow, is the diameter size. And these eddies, because of the energy they get stretched, it is like bacteria, they get split into two bigger one and smaller one like that. But bacteria of same size, they will be split into and they will increase in number. In the same way here, these eddies, larger eddies, they get split into smaller and smaller and smaller eddies like that. The energy gets passed on to the smallest eddy in micro scale, macro to micro. And finally gets dissipated into heat. Okay, this is what is called as energy cascade. Okay, then what is the problem? If I want to have the complete history of turbulent flow, we have to catch the smallest size eddy. Okay, this is what is called as Kolmogorov scale. Okay, so it will be the smallest eddy is micro range, right? So I have to catch or capture the details of the smallest eddy. Then only I can have the clear picture of the turbulent flow. These are called length scales. From the biggest eddy to smallest eddy, I have to capture the details. For that purpose, I should have the most fine grid I should have. Okay, so sometimes a 1 mm by 1 mm also, it needs some 10 power 6 grid points. So it should be such fine grid I have to capture all the details. Okay, this is length scale. And coming to time scale, I have to the life of each eddy is to be captured. So for that, time step must be in microseconds. Okay, this is the main problem with solving this. And if we can solve Navier-Stokes equations for turbulent flows, catching all length and time scales, This is called as DNS, means direct numerical simulation. This is called as direct numerical simulation. Okay, but so we need supercomputers for that. Even supercomputers which are there in US also may not be sufficient for solving normal problems. Very, very small problems we can solve for direct numerical simulation. But still people are doing that, not in India, right? In abroad only, where the supercomputers are there, so that they can have some benchmark results to compare with smaller models, simple models. Okay, so for that they are working with DNS, but here we are, nobody is working in DNS. Okay, so there are many methods came in between DNS and whatever we are going to learn. Actually, this okay, Reynolds came actually. Okay, Reynolds, he created Reynolds averaged Navier-Stokes equations. Okay, this is called RANS, Reynolds average and Navier-Stokes equations. So because why the concept is, if you take if you keep a probe any place, okay, and if you record it, suppose anemometer, a hot wire anemometer or laser Doppler velocimeter, whatever is there, if you keep the probe at a particular point in a turbulent flow, if this is the velocity and this is the time, right? So you are going to get some fluctuating component like this. And if you take the average of this, okay, so this is what is called as average velocity. And U is called as instantaneous velocity. At any particular time, whatever be the velocity, that is called as instantaneous velocity. And U bar is average velocity. So at any point, the instantaneous velocity is equal to U bar plus some U dash, where U dash is fluctuating component of velocity. Okay, so suppose at a particular point, this is U dash. Okay. So this is the way the fluctuating component when you have an instantaneous velocity at any time is equal to average velocity plus fluctuating velocity. And how this average velocity is defined, if you take a particular time period, so maybe T naught and T naught plus T, and this is T, then integral 1 by T, T naught to T naught plus T u dt. Okay, this is the way the average velocity is defined. Okay, and now if I want to find out the average velocity of u dash, and what will it be?
0.
0. Because the fluctuation, sometimes it will be positive, sometimes it will be negative, and for a long period, if you take the average of a fluctuating component is 0. Okay, and so there are some rules of averaging. So you can prove these things actually. Okay, suppose if I want to have average of sum of two components, you can prove that using that first principles, and this can be u bar plus t bar. And if I take average of average, this will be average only. Okay. And if I want to have derivative of average of a derivative, okay, this is equal to derivative of the average. Similarly, integral average of the integral, if I take, it will be integral of the average. Okay, these are simple only, and The problem comes, these are all linear terms, okay? So the problem comes when there is non-linearity. So if I have UV, okay, so UV bar I want. So U is U bar plus U dash, and V is V bar plus V dash, and I want average of this. So this is like U bar V bar plus U dash V bar plus U dash V bar like this. And this can be written as U bar V bar bar plus U dash V bar bar plus U dash V bar bar plus U dash like this. And so if I take this, and U bar is a constant, V bar is a constant actually, because it is an average, it is a constant value. And anyhow, average of average is average. This will be U bar V bar only. Plus this is written as V bar is a constant, I can take out U dash bar plus U bar V dash bar plus U dash V dash bar. But we know that average of fluctuating component is 0. And here also average of fluctuating component is 0. So this will become U bar V bar plus U dash V dash bar. Okay, this is the problem actually. I will have some additional term will come here. UV bar is not U bar V bar only. So there will be U dash V dash bar additional term will come. Okay, so similarly, if I have U square bar, because U square UV you will get in the equation. In the same way, you can write U bar plus U dash whole square bar is equal to U bar square plus 2U bar U dash plus U dash square bar. So this will be U bar square plus again this will average of this will become 0, then will be U dash square bar. Okay, this will be additional term will come. Okay, so what happens when you do the averaging of the Navier-Stokes equations? Okay, I want to do what is called as RANS, Reynolds average and Navier-Stokes equations. I will take unsteady, URI, unsteady Reynolds.
Sir, in previous slide, the 2U.
Yeah.
So the 2U bar into U dash will be 0.
Yeah, this will become, it will become 2U bar, okay, U bar square bar, 2U bar U dash bar plus U dash square bar. Okay, so this will be U bar square.
Yes, sir, understood.
U bar is constant, U dash bar, and this will become 0. This is not 0.
Yes, sir.
Okay.
So why it is not 0? V dash bar, sir?
U dash square is always positive. When it is U dash is negative, also positive.
Yes,
U
yes,
bar,
sir.
okay, right.
Mm-hmm.
Okay. So if I take this, okay, I'll for simplicity I will take incompressible. Okay, suppose I take a continuity. We'll go off U bar plus U dash. Okay. And now if I take average of our whole thing,
Sir, Navier-Stokes equation is can be used for viscous.
yeah, we'll do. This is a continuity I'm doing, right?
Yes, sir. But sir,
Navier-Stokes equation is the viscous equation only.
yes, sir.
If
And
it is not viscous, we call it as Euler's equation.
yes, sir. Yes, sir.
Okay, like this it will become dou u bar by dou x. This will become 0. This will become 0. This will become 0. That's dou v bar by dou y. That's dou w bar by dou z equal to 0. So there will not be any problem. This equation, if you see, this is with instantaneous velocities, and we are getting some equivalent equation with average velocities. That's all. These, because of the fluctuations, so the continuity equation will not change. Only instantaneous velocities are replaced by average velocities. Okay, this is the continuity equation with time averaged. Okay, velocities. Okay, this is for continuity equation. When you take momentum equation,
Sir, why the average is comes?
yes,
Sir, in second, we have taken the average, na?
yeah. So average of this I am taking. Okay, so average of each term will come, and average of the derivative of the average. So it will become like this, and again sum of these two, u bar bar plus u dash bar. U bar bar is u bar, u dash bar is, this will become 0.
And sir, Navier-Stokes equation is valid only for incompressible flows.
No. Navier-Stokes equation is the most generalized flow. And if it is a compressible flow, I will have dou of rho u by dou x plus dou of rho v by dou y like that, plus dou rho by dou t. Okay, this is the continuity equation for compressible flow. I am taking for incompressible flow just del dot v equal to 0.
Yes, sir.
Okay.
Yes, sir.
Like that. Okay, now if I take the momentum equation, so I take I take simple equation. Okay. So x momentum equation if I take, and if I take the average of this and this, so each term separately can be averaged. So it will become, rho is a constant here, rho dou u bar by dou t plus dou by dou x of, what happens, u square bar is u bar square plus u dash square bar. Do you remember that? And uv bar, u bar v or uv bar plus u dash v dash bar is equal to, these are linear terms, no problem. It will be just like this. Tau x bar by dou plus dou tau x bar by dou y plus dou v. Okay. So as long as there is a single term, yeah, with instantaneous velocity, just replaced by average velocity. So no problem. It will come like this. But these are the additional terms we will get. So what I do is, I will rewrite it. Okay. These additional terms, whichever I got, I take it to the right side. It will become dou p by dou x. It's dou by dou x of tau xx minus dou u dash square bar. It's dou by dou y of tau xy minus dou u dash dash. Yes, dou like this. Okay, this
Sir,
is
how it comes?
this rho u dash rho into u dash square bar. I am bringing it to the right side, and rho u dash v dash bar also I am bringing it to the right side. This is in dou by dou x. This is in dou by dou y. Am I clear?
Okay.
Same
Yes,
things
sir.
are written here. Only thing, those two terms I am taking to the right hand side. Okay, here this is the way it gets modified. Okay, and so I got some additional terms. Okay, these are the additional terms, and actually this is a stress term. Okay, this is a stress term, and so I have got some additional stresses because of the fluctuating components. Am I clear? And these additional stresses due to fluctuating components are called as Reynolds stresses or eddy stresses or some turbulent stresses or apparent stresses. Okay, some different names are given like that, but Reynolds stresses is the most popular one. Okay, so all turbulent stresses. And so tau t if I write, so I will have minus u dash square bar minus rho u dash v dash bar minus rho u dash. If it is z component is there, this component will be there, and in the y momentum equation, I will have like this. By symmetry, you can write rho v dash square bar minus rho v dash w dash bar minus rho v dash w dash bar minus rho v dash w dash minus rho w dash bar. These are called as Reynolds stresses.
So can you move previous slide, sir?
Yeah, sure. This is one. So rho
Yes,
u dash square bar, rho u dash v dash bar, and if I have dou by dou z, rho u dash w dash bar I will get. That is the x momentum equation. These three components I will get. Same
yes,
way
sir.
I will get. These are called as Reynolds stresses. Okay. So this is the. So I have how many components are there?
9.
9 components, just like laminar stresses. But how many unknowns? Again, symmetry because of the isotropy and homogeneity. So I will have only 6 unknowns. Okay, like minus rho u dash square bar, minus rho v dash square bar, minus rho w dash square bar, minus rho u dash v dash bar, minus rho u dash w dash bar, minus rho v dash w dash. Okay, so this gets repeated u dash v dash, u dash w dash, and v dash w dash. So there will be 6 unknowns. So this is what is called as turbulence closure problem. So URANS, Reynolds average and average equations, involves 6 unknowns of Reynolds stresses. Okay, this is the problem. I have 6 additional unknowns are there. So how to resolve this? This actually creates what is called as closure problem, turbulence closure problem. This only leads us to turbulence modeling. Okay, before going to modeling, because these are Reynolds stresses are there, people try to derive expressions for Reynolds stresses. Okay. Okay, these are big derivations. Just I will give you the method of how to get it. Okay, okay, this is what is turbulence and why it is why turbulence. Okay, we have so all natural flows, as I told, turbulence from the interior of biological cells to circulatory and respiratory systems of living creatures to countless technological devices and household appliances of modern society to geophysical and astrophysical phenomena, including planetary interiors, oceans and atmospheres and stellar physics, and finally galactic and even supergalactic scales. Okay, all these involve turbulence. And so it will have the characteristics are randomness and fluctuation, nonlinearity, diffusion, vorticity, eddies, energy cascade, dissipation, three-dimensional coherent structures, a broad range of length and time scales, which makes the DNS very difficult. And so there are many people worked over a period of the history is given by Bosines, Reynolds, Prantl, Taylor, Kolmogorov, Batchelor, Krechanan, Launder, Lumley, Wilcox, Pollard, and many more are there. When we study turbulence models, you can see models developed by many of these researchers. And we know that in external flows, when Reynolds number is greater than 5 into 10 power 5, that is along a surface, then there will be turbulence. And if around an obstacle, if you take, it is 2 into 10 power 5, 4. And if it is internal flows like pipe flows, it is 2300. These are called as critical Reynolds numbers. And if it is a natural convection, if Rayleigh number is greater than 10 power 9, you will have turbulence. That you have studied.
So
You have
can,
studied. Yes.
sir, for external flows along a surface and along around
This
a
is along
substrate?
a plate. This is along a plate. If it is around a cylinder or something like that, it is 2 into 10 power.
Yes, sir.
Okay. Along a plate, 5 into 10 power 5 is the critical Reynolds number.
Yes, sir.
And so U is equal to U bar plus U dash. And this is a steady flow. And there can be unsteady flow also. If instantaneous velocity is varying with time, it is unsteady flow. But here also you write instantaneous velocity is sum of average velocity and fluctuating component. So here it is given, this is the time average. Okay. And all these, whatever I told, they are there. And this is in tensor form. It is straight away, right? Dou ui by dou xi. Instead of writing three components, he is writing just dou ui by dou xi equal to 0. This is continuity. So dou ui plus u dash by dou xi is equal to 0. If I take the average of it, dou ui bar plus ui dash bar by dou xi is equal to 0, and this is 0. So this will become dou ui bar by dou xi equal to 0. Okay, I need not write three components. Only one component I can write. And so this is a bit simple if you write in tensor form. And similarly, this is the tensor form of Navier-Stokes equation. And if I write here, like ui, uj, xj, so ui bar, so in tensor form, you need not write all three components, only one component like ui only you write. Okay, this comes like this. And here, this is the one I will get. Okay, instead of writing a matrix, I will just like this. Now tau t is equal to minus rho ui dash uj dash bar. Okay, like this. So how many components it will have? Ui, uj, right? So it will have 9 components. It's like second order tensor. So this is the Reynolds stress. And if you do for energy equation, you will get something like this. Okay, so we don't worry about that. Just we have to know how to get it. So here also, yeah, this is the Reynolds stress matrix which I have drawn. Okay, this is laminar stress. And this is the turbulence closure problem, what I was discussing about. And okay, now if I want to have equations for Reynolds stress, okay, how to get the equations for Reynolds stress? Now here, this is the Navier-Stokes equation with the k as the suffix. Instead of I am writing k. And to this, I multiply by ui. And I am going to get one equation. Similarly, ith equation is multiplied by kth velocity component. Then you will get like this. I will tell you what is the logic. And then if you add these two, I'm going to get this equation. Means like I have dou u by dou t equation and dou v by dou t equation, and multiply this by v, multiply this by u, and add it, you are going to get dou of uv by dou t. Okay, so that is the logic to get the equation for the product. Okay, and these are instantaneous velocities. Similarly, you average it, and I'm going to get dou by dou t of like this, and subtract this from this, I'm going to get dou of u dash v dash bar by dou t. So this is the equation for Reynolds stress. Like this, okay, a lot of mathematics is there. Logic is that, okay, so kth equation is multiplied by ui, dou ui into dou uk by dou t. Similarly, dou ui by dou t is multiplied by uk, and if I add these two, I'm going to get dou by dou t of rho ui uk. Okay, so only thing is here there will be third order tensors will be there in this equation. There will be third order tensors. That is the main problem. Okay, and then again you get the average of them. You are going to get by substituting this, you are getting the average equation, and then okay, this is the equation you will get, and subtract this, subtracting the last equation from the instantaneous equation, I'm going to get an equation like this. This is the Reynolds stress equation. You can see a very, very large equation, and there will be third order tensors will be there. Okay, so this is the main problem. And okay, there are RHS terms here. Suppose u dash dou p dash by dou x. If I want to write it, this is equal to dou of pu by dou x minus p dou u by dou x. Like that I will write. Okay, so this is there are two terms I will get. In the same way, these also stress terms also are written like that. And if I substitute, I'm going to get this particular equation. This is called as Reynolds stress equation. And this is written in this way in compact form. And some of the terms are written as D, some as R, and some as P, and some as epsilon. Okay, so these terms are written in that way. It's a compact form. And what is djk, rak, pik, epsilon ik is written here. Why they are separated is one represents diffusion, one represents redistribution or energy exchange, another represents production or generation, and one represents dissipation. Okay, so each has some physical significance for each term. Okay, so to understand that, they have separated it and given separate names like that. Okay, so here, this is the equation. This is the Reynolds stress equation. So what happens is, here there will be many more additional terms will come. And how many more equations? Actually, these are 6 equations. Reynolds stress equations, how many you will get? 6 equations for each unknown. One u dash v dash bar, u dash w dash bar, like v dash w dash bar, u dash square bar, v dash square bar, like that. I will get 6 equations. But what happens is, there will be additional unknowns will come here because of this. Suppose this is the third order tensor. How many components will have? It will have 27 components. And out of 27 components, 10 will be unknowns because of isotropy and homogeneity. So here, there are 3 additional terms are there. And this term has 6 unknowns, this term has 6 unknowns, and this term has 10 unknowns. Totally 22 new unknowns will come. Okay, that is the problem with Reynolds stress equation. Okay, so then if I want to get equations for these unknowns, there will be maybe 100 unknowns may come into picture. So this is the way I cannot go on. Okay, so this ought to be modeled. Okay, that's why it needs modeling. So instead of doing modeling of Reynolds stress equation where I have 22 unknowns, So people are working with this also, Reynolds stress equation. These are called as Reynolds stress models, RSM. Okay. These are Reynolds stress models. Okay, now this fellow Bossinus has come into picture. Well, this Bossinus hypothesis is famous in even natural convection also. Did you remember
Yes, sir.
Bossinus hypothesis? Here also, but that Bossinus hypothesis is different. Person is same, but there a different in the natural convection, and here in turbulence, it is different. So Bossinus. So what he has done is, if you take laminar stress, laminar viscosity, no, stress only, laminar stress, it will become mu into r mu rho. This is mu only, right? So dou ui by dou xj plus dou uj by dou xi. Okay, these are the laminar stresses, if you remember. So in the same lines, Bossinus has defined turbulent stresses as rho mu t. Okay, I will write L here. Dou ui by dou xj minus dou uj by dou xi minus 2/3 delta ij k. This additional one he has put where k is turbulent kinetic energy, which is equal to like this, or half into u dash square bar plus u dash square bar. Okay. This is what is called as turbulent kinetic energy. Okay, so in the same lines where nu t now is called as eddy viscosity or turbulent viscosity, like this. So the finally it lands up in knowing, if I know what is nu t, that is sufficient, and k also. Okay, k also, and k, if I know Reynolds stresses, I know k. Okay. Okay, this is what is called as Bossinus hypothesis. So now the attention is paid on finding out the eddy viscosity or turbulent viscosity. So this is the closure problem of turbulence. This is the Bossinus hypothesis. And so here various models are listed here. Turbulence models, we have DNS, direct numerical simulation. There is what is called as LES. This is called as large eddy simulation. And there is one more called as detached eddy simulation. Okay, large eddy simulation means, okay, it is given in the later slides. Okay, okay, this is what is called an energy cascade. Large scale eddies, the goes from energy goes to the smaller, and finally in the smaller scales it dissipates, right? Dissipation of energy. This is called as energy cascade. So if I can resolve all the scales, all the sizes of the eddies, this is called as direct numerical simulation, right? Large eddy simulation is larger eddies, if I can find out and model the smaller size eddies, this is called as large eddy simulation. Actually, presently, Indian research people are working in IITs on large eddy simulation. Okay, because okay, this also needs high-speed computers. So the computers that we have, sometimes in IITs they will do parallel computing. Okay, so many processes they will make it as a parallel processor, and then you can resolve this. Okay, larger eddies are resolved and smaller eddies are modeled. And RANS means the complete all eddies are modeled only. This is called as energy cascade. So DNS stands for direct numerical simulation. This corresponds to solving NSCs on digital computer using sufficient resolution to capture all physically important scales from the largest to the spatial scales. And so these scales are given something like this. So here, the total number of operations normally depend on Reynolds number to the power of 11 by 4. On top of this, you have to do hundreds of operations per point. Okay, so here you can see it takes a very, very large time. And there is what is called as very large eddy simulation. Okay, this corresponds to a coarse grid large eddy simulation and now is viewed as being equivalent to URI, that is unsteady Reynolds average and highest simulation. And then large eddy simulation. Here, the LES, the large scale energy carrying motion, is directly simulated, while the small scales are modeled. And similarly, DES, we use LES in the outside, but RANS in the boundary layer. In the boundary layer, we use RANS equation. Other side, outside, it will large eddy simulation. This is called as detached eddy simulation. Okay, just you understand the concept.
Can you explain again, sir, detached eddy?
Detached eddy simulation, if you take, suppose if you study turbulent flows, we have laminar sublayer and buffer layer and the turbulent layer like that, isn't it? There are 3 layers and 2 layers. 2 layers means only laminar sublayer and turbulent layer. In the laminar sublayer, the eddies are very small, right? In turbulent layer, there will be eddies are large. So in the laminar sublayer, you can use Reynolds average and Navier-Stokes equations in the boundary layer, and outside you use large eddy simulation. Okay, RANS
Yes,
approaches in near wall regions where LES used in the high resolution.
sure, but in previous slides, sir, RANS was used for large eddies.
RANS is always used for smaller eddies only.
Okay, sir.
Right? Okay, RANS is used to catch, okay, in general, all, okay, RANS means it's a model. RANS is completely modeled equation. Okay, so I will show you what is that modeling. Okay, so this RANS, I need eddy viscosity, right? So these are also called as eddy viscosity models. Eddy viscosity models are classified like algebraic models or zero equation models, 1 equation model, 2 equation model, algebraic stress model, like that various models are there. Okay, what do we mean by this? Okay, so mu t is to be modeled. Okay. So there are, these are called as eddy viscosity models. RANS models are also called as eddy viscosity models. There are what are called as zero equation models. Okay. So if mu t is calculated using algebraic equations, these are called as zero equation models. I don't know, normally in fluid mechanics, right? When you study, have you studied turbulence in your fluid dynamics? Anybody can answer me? Your advanced fluid dynamics, anything is talked about turbulence or not?
No, sir.
No, sir.
No. Okay. So zero equation models, there are 2 types normally. Prandtl's mixing length model and von Karman's mixing length model. Okay, there are 2 models. It is just simple algebraic relations. We can find out mu t, and then you can find out the stresses. These are called zero equation models. There are what are called as one equation models. If one ordinary differential equation is to be solved to get nu t, right? These are called as, okay, not one equation, this is half equation. These are called half equation model. In addition to Navier-Stokes equations, I need to solve one additional ordinary differential equation, then it is called half equation model. Then we have what are called as one equation models. That is one additional partial differential equation is to be solved. Okay, then two equation models. So two additional partial differential equations are to be solved. Okay, these are very popular. There are two types of models are popular. One is K epsilon models and another is K omega model. Okay, so there will be one equation for K, one equation for epsilon. So if you remember in the Reynolds stress equation, we got one parameter as epsilon, which is called as dissipation. This is turbulent kinetic energy. And everything, normally two equation models, we represent, this is called as velocity scale, this is length scale. Velocity scale, length scale. There are two equations are to be solved for different scales. And so K epsilon model is the more popular, and K omega is recently becoming popular. This is brought by Wilcox, and this is brought by Launder and Spalding. And a lot of variations in K epsilon also are coming, standard K epsilon, RNG K epsilon, and realizable K epsilon. Like that, a lot of things are coming. Okay, what is that actually? Why it is called as model and all, we'll see. And okay, suppose here nu t can be written as E mu K square by epsilon. Okay. So K is solved from the K equation, epsilon is solved from the epsilon equation, and C mu is a constant to be modeled. So if I can solve this K and epsilon equations, I can get nu t. If I get nu t, I know the turbulent stress. Okay. So in that way, we do this. Okay.
Give me, sir.
Yes.
Sir, as we have seen in the also in one of the graph, we have seen the initial velocity is matters a lot. Like if there is a change in initial velocity, then
Yeah,
the
always.
final.
See, always. If uh, many times I told you the boundary conditions. The boundary conditions are very important because the boundary conditions only influence the interior, right? So any small change in the boundary condition, the whole interior behavior will be different. Am I right? Initial velocity is entry velocity. If entry velocity is different, the whole flow is different, right?
So, sir, how we will know that how much variation can is good?
That is in relation to the inlet velocity, how much variation you get in the result.
No, sir. I mean, like if we want to do something, for example, if I'm going for inlet velocity of 2 meter per second,
Okay.
so how much can I expect that my result will be good for the
That's
error I have
why
solved?
sometimes it is not better to deal with absolute things. It is if you deal with non-dimensional quantities, right? I think in heat transfer, you non-dimensionalize the equations, right? So if you
Yes.
non-dimensionalize the equations, then there will not be any problem, even
Okay,
if
sir.
there is a change. Okay. because the non-dimensional components like Reynolds number, Prandtl number, Nusselt number, those things, they will not get affected by the velocity. Only non-dimensional things, right? So then we need not worry much. It will not depend on absolute velocities. It depends on the ratios, right? The non-dimensional components. Okay, so this is the Bosnian-Sky pulses, as I told. This is laminar and this is turbulent. And eddy viscosity models, I have to model this. And these are the various models like algebraic models, 1 equation, 2 equation, and 4 equation models, Reynolds stress models. And so the unsteady Navier-Stokes equation. Okay, this actually I didn't properly organize. Sometimes some things are repeated, right? These are the answer equations, additional unknowns, turbulence models. Okay, these are various equations like zero equation models will get like this. Zero equation Rance. This is another model, Sebeki-Smith model. This is also zero equation Rance model. And Baldwin-Lomax, this is also zero equation model. And 1 equation model, we have Baldwin-Barth model. These are popular only. As I told, in the 1 equation model, Spalart-Almaraz model. These are there in the options of free and PQC. So here it is given some advantage and disadvantage of 1 equation model. And derivation of K epsilon model also is given. So here, because this is the K epsilon K turbulent kinetic energy defined. So what you do is, again, you multiply dou U by dou T if you have, you multiply with U. Okay. So then U dou U by dou T will be there into 2. So 2U dou U by dou T, it will become dou of U square by dou T. So then you average it, dou of U square bar will come. And if you subtract, then dou of U dash square bar, like that you will get. So in that way, you can get the turbulent kinetic energy equation. And this is the equation. And similarly, you can get the equation for dissipation. And you are going to get, this is epsilon equation derivation is given. You can just, because many books, it will not have these derivations. I have given this here. Okay, so here, if you see these equations, these are written like transport equations. Okay, though it's a big equation like this is rearranged, right, and modeled to get the equation similar to our momentum equation, energy equation, like that. So this is this way: unsteady term, convection term, diffusion term, and source terms. So in this way, they are written. And these are the constants like C epsilon 1, C epsilon 2. Okay. So these are the constants to be modeled. Means, like if you remember in the forced convection, we know that Nusselt number is equal to function of Reynolds number, Prandtl number. So what we will get is nu is equal to some C r e to the power of n, p r to the power of n. So C, m, n are to be modeled. So based on your practical application, you will have heat transfer data books, and you will be given C value, M value, N value for different conditions, right? For different values of Reynolds number or Prandtl number, like that. In the same way, these constants are to be modeled. Okay. So standard K epsilon, there will be some values, and some other model, there will be different values, and it varies from case to case. So K epsilon model, these are the equations. K omega model, these are the equations. And these are the constants you can see. C epsilon 1, 1.44, C epsilon 2, 1.92, C mu, 0.09. And here sigma K, sigma epsilon are there. So these are the values. If you use these values, that is called as standard K epsilon model. And if you have a separate problem you are solving, and if you have your experimental results, and you can model it, you can find out what constants will match your experimental results. So you can have a paper, and you can have a benchmark problem, and you can say these are the constants which are suitable for this particular problem. So other people also refer you and cite your paper, and they will use your model. Okay, and it will come with your name, model of this fellow, like that. So these are the two equation models, and there is a four equation model. This is not popular. It's just I have given literature is there, and here I have given some tables. Okay, these are just repeated. Okay, here comparison of Rand's turbulence models. Okay, model its strengths and weaknesses. Spalart Almaros, standard K-epsilon, RNG K-epsilon, realizable K-epsilon, Reynolds stress models. Okay, this is one slide from another paper I have taken. These are the advantages and disadvantages of different models. You can just go through. So for a particular problem, if you want to know which model works well, right, you have to depend on the literature only. There is no other way, right? Sometimes you will apply all the models and you can find out and say which model is suitable for your particular problem. So you can publish a paper. Okay, this is the way you can go through this. I will give you the material.
So during problem solving in simulation, like so, how it will come to know which model is good
Yeah,
for
that's what.
this?
Okay, if similar problems are solved in literature using a particular model, they will suggest you, okay, for this type of problems, you use this model and you can use it. If you don't know which model will be good, you have to experiment it. Okay, work with different models and see which model is suitable for your problem. That's why you should have the main thing in CFD is validation. Okay, there should be some experimental result or some other result which is to be compared with your model. Okay, so you have to see, use a model and compare with the existing experimental result, and you see whether it is tallying or not. Okay, if it is working well, you can continue or work with other models and see which is the suitable model for your particular problem. Once you understand it, this model works, then you can vary the parameters, velocities or viscosities or something like that, and you can predict for the unknowns using the same model. Am I clear?
So please explain again.
What I am telling is you will have some experimental results for some cases. Okay, because experiments cannot be done for all cases. For some cases, experiments are done, and you are doing modeling for that. So you use some turbulence model and compare with those results. If it is not working, you change the model and compare. And once you come to a model which gives some reasonable results with the experiments, then you say for this particular application, this model works. And once you prove that this model works for this type of practical problem, then you can change the parameters. You can change the size, you can change the velocity, you can change the anything. Okay, fluid you can change, anything you can change, and you can predict the for the unknown values which are not experimented. So first
Okay,
you have to compare with the benchmark problem and find out which model works for your problem, and then you can predict for the unknown things. Am I clear?
yes, sir.
Okay, so that is the way we have to proceed. Any other questions? There is nothing. These are, I will just make it better. Some repeated slides I will remove and make it better, and I will send you. Okay, then we will go for the story, a small story. What makes you happy story? A troubled rich woman, a rich woman is there and she is not happy, and she went to her psychiatrist complaining she isn't happy. A beautiful, expensively dressed lady who complained to her psychiatrist that she felt that the whole life was empty, it had no meaning. So the lady went to visit a counselor to seek out happiness. The counselor called over an old lady who cleaned the office floors and then said to the rich lady, I am going to ask Mary, that is the who is working there, here to tell you how she found happiness. All I want you to do is listen to her. Okay, there is a sweeper lady is there. She is always happy, and she called that lady to this rich lady, and he told that lady sweeper will explain you, right, how you can be happy. So the old lady put down her broom, sat on a chair, and told her story. Well, my husband died of malaria, and 3 months later, my only son was killed by a car. I had nobody. I had nothing left. I couldn't sleep. I couldn't eat. I never smiled at anyone. I even thought of taking my own life to commit suicide. Then one evening, a little kitten followed me home from work. Somehow I felt sorry for that kitten. It was cold outside, so I decided to let the kitten in. I got it some milk, and the kitten licked the plate clean. Then it purred and rubbed against my leg, and for the first time in months, I smiled. Then I started to think, if helping a little kitten could make me smile, maybe doing something for people could make me happy. So the next day, I baked some biscuits and took them to a neighbor who was sick in bed. He cried after seeing me and taking the biscuits. He cried and said that he didn't have an affectionate attention and nice food for the last few years. Every day I tried to do something nice for someone. It made me so happy to see them happy. Today I don't know of anybody who sleeps and eats better than I do. I have found happiness by giving it to others. When she heard that, the rich lady cried. She had everything that money could buy, but she had lost the things which money cannot buy. The beauty of life does not depend on how happy you are, but on how happy others can be because of you. Happiness is not a destination, it's a journey. Happiness is not tomorrow, it is now. Happiness is not a dependency, it is a decision. Happiness is what you are, not what you have. Okay, thank you. Thank you very much.
Thank you,
Thank you,
sir.
sir.
Thank you. See you.
Thank you, sir.
Thank you.
Thank you, sir. Excuse me, sir.
Yes.
Uh,